My name is Konrad Hofmeier. Today I'm going to talk about local first apps using Postgres logical replication, and specifically how we built a high scalability sync engine with dynamic partial replication to facilitate local first app architecture. So I'm going to give a bit of background to this project and then walk through some of the system design, architecture, and implementation details, and then also spoke about how we worked with Postgres logical replication and what some of the specific challenges are that we had to solve there. So first of all, just starting with what local first architecture is. So you may have heard about this. It has some significant overlap with offline first, which is an idea that has been around for the last 10 plus years. But local first is an architecture where app code works directly with a client-side embedded database, which then automatically syncs with a backend database in the background. So reads and writes go to the local database first. And this has significant benefits for both app developers as well as end users. So for app developers, because you're working with a local database, you don't have to deal with retrieving data via API and dealing with caching of API calls and things like that. And therefore, it also simplifies the backend because the complexity of the APIs that you have to develop is reduced significantly because the data transfer basically gets taken care of by the sync engine. And then related to that, you also get lower backend compute load, dependency, and cost. And then for the end user, because you're reading and writing to a local database that's on the user's device, it's near zero latency. So you basically get an instantly reactive UX. And for the same reason, the apps are, because you're working with a local database, the apps are always available. So you're not dependent on a network API. You read and write to the local database so they can actually work offline as well. And then by virtue of using a sync engine, as a side effect, you can also get real-time multi-user collaboration. So I think these are really good reasons why local first architecture is getting more and more traction. So when building this sync engine, as far as why we chose to focus on Postgres, for the past 10 plus years, our company Journey Apps has been, our first product was a full stack platform for offline first industrial apps. And we were thinking of spinning off our standalone, our sync engine as a standalone product, which came to be called PowerSync. And we were quite familiar with some of the NoSQL-based sync engines that are on the market. So for example, MongoDB and Atlas Device Sync and Realm, and then CouchDB, PouchDB. But sort of late 2022, when we started seriously looking into this, it didn't seem like there was really sort of a mature equivalent sync engine for PostgreSQL that can also sync to a client-side embedded SQL-based database such as SQLite. And there's also other reasons why we decided to focus on Postgres and SQLite. We are big fans of SQL, and of course, it's, as a language, remains more universal and it's very effective for advanced queries. And then SQLite is hard to beat when it comes to performance, flexibility, and advanced functionality, and also just how battle-tested it is. So the famous statistic is that there's 1 trillion SQLite databases in active use. It's, of course, in every smartphone and a lot of other places. Our architecture does allow for swapping out the SQLite database with another client-side database, but initially we thought it would be best to start by focusing on SQLite. So I thought it would be helpful to sort of see how we worked with Postgres and built this around Postgres. So I'm going to walk through the design, architecture, and implementation of this PowerSync sync engine that we built. And these are some of the things I'm going to focus on. I'm going to start with design objectives and high-level architecture. So one of our main design objectives was to treat the Postgres database as sacrosanct. So a big thing there was to work with standard Postgres databases in a non-invasive way. So require minimal to no changes to the schema, the configuration. And then related to that, we didn't want to bypass the developer's existing business logic, authorization, and validation. We figured that, for adopting this kind of sync engine, developers may be averse to it if we're writing directly back into their Postgres database. So we wanted to avoid that in our architecture. Dynamic partial replication was a really important capability. That's kind of a linchpin capability of these kinds of sync engines. It's not very useful if you have a large Postgres database in the backend, but you can't actually effectively sync a subset of the data to the client side. And then low maintenance. We wanted the system to be very low maintenance, especially when it comes to schema evolution, and then also providing strong consistency guarantees. So early on in the architecture, we made a big decision, which is to separate the read or download path from the write and upload path. So for the read path, we built a middleware service, which is called the PowerSync service, which interfaces with Postgres logical replication, and then does the dynamic partial replication of the data to the clients. But then for the write path, we decided to make all the writes go through the developer's existing backend so that they can utilize their existing business logic and validations and things like that. So zooming in a bit on the read path, dynamic partial replication. So of course the objective there is to get a relevant subset of the data to users. And if you sort of just start first thinking about it, a naive approach might be to allow the clients to make sort of arbitrary database queries, maybe within some sort of permission policy framework, and attempt to keep their result sets in sync. But if you think about this kind of scenario where you have a local first app architecture, you can have thousands or millions of users that can go online and offline at any time. They can come back online hours later, days later, or even weeks later. And then you would basically have to sync the deltas for their specific queries relative to their specific current sync state. And you can multiply that by millions of users potentially, or tens of thousands of users. So that quickly becomes problematic for high scalability. So the design that we went with was to allow for predefining buckets of data, and then buckets of data can be shared between users where applicable, and then efficiently tracking changes to data in those buckets. So whenever we detect a change in the Postgres database through the logical replication stream, we basically figure out which buckets are affected by that change, and then we update the operation history for that particular buckets. And then how it actually works is the developer that uses this parsing sync system, they start by defining declarative sync rules with a single syntax where they group data into buckets. So the buckets can reference parameters from the client. So you can see there that they can access parameters from the JWT authentication payload. They can do a parameter query, or they can retrieve additional parameters that are needed from elsewhere in the Postgres database. And then they have their data queries where they query the actual data that is included for that particular bucket. And then, of course, they can define multiple of these buckets. And then what the system does is, based on those sync rules that have been defined, it replicates and pre-processes data from Postgres. We perform the replication initially by taking a snapshot of the tables defined in the sync rules with regular SQL queries, and then update them incrementally with logical replication. And then we have our own checkpoint system that keeps track of Postgres LSNs in the replication stream, which I'll mention more about later. And there's a lot of sort of analogous aspects of the implementation of this system versus some of the internals of Postgres, like the checkpoint system. One of the big decisions that we made as far as our design objective to make this system not invasive to Postgres was to store the operation history inside of the parsing service middleware. So we basically have a pluggable storage layer there where we store the operation history. And so effectively we're creating a rebuildable persistent cache outside of Postgres. And we keep the Postgres database clean so that we don't put a bunch of metadata and schema changes in the Postgres database. We store the recent history of operations for each row. The reason why it's recent history is that we compact the operation history so that you don't have an infinitely growing operation history. We represent the rows as JSON in the middleware storage. And then very importantly, the operations are indexed by an operation ID, which is a strictly incrementing integer ID, which allows us to query an ordered list of operations very efficiently. And then the users are authenticated using JWTs. So I think the details of that are not as important, so I'm kind of going to skip over that. But once the users are authenticated, then the system does streaming sync of the bucket data from the parsing service to the clients. So it basically figures out, when a user is authenticated, it figures out, okay, which buckets are applicable to this user, and then it keeps a connection open and continuously streams any operations added to those buckets, and then it also takes into account changes in the bucket configuration, like added and removed buckets. And on the client side, that data is then persisted in SQLite. So we have a type mapping from the Postgres types to the SQLite types. Of course, SQLite has a very, very limited type system, only a handful of types. The replicated data is stored in a schemaless format in SQLite. So the application does then define a client-side schema with tables, columns, and indices, which is, of course, based on the Postgres schema and the sync rules, and you can automatically generate that in that way. And then the schema is applied as SQLite views on top of the schemaless data. And then the client SDK also provides live reactive query hooks, like, for example, React hooks to update the UI when data changes. So that's the read path. So that explains how we do the dynamic partial replication from Postgres to SQLite. And then the next question is, okay, what does the write path look like? Because it's active replication. If you make changes on the SQLite side, how do those changes make it back to Postgres? And as I mentioned, we send those writes through the developer's existing backend. So the developer can just write to the local SQLite database. But then the client SDK automatically puts those writes onto an upload queue. And then the developer has to define a function for uploading those changes to their backend. And from there, writing the changes to Postgres. So the developer gatekeeps the writing to Postgres. They don't have to care about retrying a network failure logic. The client SDK does take care of that. Yeah, so that's the right path. And then as soon as you talk about merging changes, then the big question becomes, okay, how are you merging changes? What about conflicts? And that's where CRDTs typically come in. And one of the interesting implementation aspects is that we decided not to implement CRDTs on a protocol level. So if you're not familiar with CRDTs, conflict-free replicated data types, they're essentially a special data structure where changes can be merged in any order, and the conflicts are always resolved in a deterministic way, regardless of the order in which you merge them, so that all the replicas then converge to the same state. An alternative to CRDTs, broadly speaking, is that if you can always merge changes in the same order, and then all the replicas converge to the same state. So our system uses an architecture where there is an authoritative source of truth regarding the global order of operations, which is maintained in the middleware parsing service that is derived from the Postgres logical replication stream. So our system does not actually use CRDTs on a protocol level. So that has some upside and downside. The downside is that you don't necessarily get the sort of predefined deterministic behavior of how conflicts are resolved. But the upside is that it provides simplicity and customizability for the developer. So the developer's backend can reject and accept changes as needed, and then all the clients will converge to the server authoritative state. And then the other part of the flexibility and customizability is that the developer can also apply custom conflict resolution. And that can actually include using CRDT data structure. So even though we don't use CRDTs on a protocol level, you can use CRDT data structures stored as blob data in Postgres. So we actually have done a POC where we take the YJS CRDT for rich text editing and store the blob data in Postgres. And then guaranteeing consistency. So we keep track of write checkpoints on the server. So checkpoints have an associated operation ID and Postgres LSN. As I mentioned, the local client-side writes, the developer can just write to the SQLite database. Those writes are applied on top of the last checkpoint received from the server. So that if the app is offline and the app queries the local SQLite database, those query results reflect local mutations that have not yet been uploaded, but then they're also placed into an upload queue. And then the client retrieves the latest checkpoint from the server after it has finished uploading all the writes. So when its upload queue is empty, and those changes have been written to Postgres, then the client updates its local state to match the server state. And then that way you can see how all the clients basically converge to the server authoritative state. And in data integrity, what happens if the data gets corrupted? That's pretty simple. We just basically compute a per bucket checksum on the client and server side. And if there's a checksum mismatch, then we re-download the bucket. So tying it all together, you can see how this enables kind of an active-active replication between SQLite and Postgres in a way that is kind of not invasive to Postgres. It's sort of, you can sort of plug it in and easily remove it again, and that enables that kind of local first architecture. So logical replication is, of course, a capability in Postgres that has gone through a lot of improvements over the last several releases, and it's a really powerful capability. It has enabled a lot of really interesting solutions in the Postgres ecosystem. It's super, super useful. And of course, we wouldn't have been able to build this without logical replication. So it's a critical capability. We did run into some challenges with it. So there were some challenges where we sort of just had to make some tweaks as far as adapting it to the parsing model or architecture. And those are sort of these four that I'll just walk through. So one of them is handling schema or DDL changes. So as of the current version of Postgres, DDL changes do not get published to the logical replication stream. This may change in one of the future versions of Postgres. There is some type identifier information that is published where you can identify the column types and names. So our objective was to make the system sort of low maintenance, including regarding schema changes. So there's a few things that we did right off the bat in pursuit of that design objective. And this is one of the big reasons why we made the PowerSync protocol and client-side database storage schemaless, and then we apply SQLite views on top of the schemaless data. So schema migrations hardly affect the client-side database. And then also sync rules can apply some transformations to the Postgres data during replication. So this means that the developer can use that for backwards compatibility. So they can allow the clients to keep using an older schema even if the Postgres schema has actually changed. So that reduces the surface area that's affected by schema changes in the system. But of course, schema changes do still affect the system, especially on the replication side. There is still some surface area. So our approach was basically to try and detect wherever possible and either automatically handle or document a manual procedure for handling schema changes. So this is the list of sort of 7 schema change scenarios that we currently handle. You can see 4 out of the 7 are detected automatically, whereas 3 of them cannot be detected automatically and require developer intervention and developer action. And in 2 of the 4 that are detected automatically, we do resync the entire table. So for example, if the replica identity changes, we resync the entire table. There are some fundamental limitations as far as what we can do with the Postgres schema. For example, generated stored values are not published in the logical replication stream. But generally, this architecture works well and kind of provides predictable behavior for the majority of cases. The other challenge that we ran into was that the log sequence numbers in Postgres, we needed a monotonically increasing operation ID sequence. And initially, we actually derived that from the Postgres LSNs. But we moved away from that to a separate auto-incrementing integer sequence for a few reasons. One of the reasons was that the LSNs in the Postgres write-ahead log are not actually guaranteed to be monotonically increasing. So transaction commits are always in sequence in the write-ahead log, but operations inside each transaction can have LSN ranges that overlap with other transactions. So that was one of the reasons. The other reason was we wanted an architecture that can support sharded databases, where each Postgres instance has its own LSN sequence that has to be merged into a singular op ID sequence. So basically multiplexing. And then the last one was we need the ability to reprocess sync data, and then we need to continue the existing op ID sequence while the LSN sequence would basically still stay the same. The third thing that we had to solve was toasted values. So toast is the oversized attribute storage techniques where basically values are stored in a separate table if they exceed the page size. And then in the logical replication stream, the toasted values are only published if the value has changed. There is one exception to that, which is when you use replica identity full, then the full value of the toasted attributes are always published in the keys field on the logical replication stream. But we obviously can't guarantee that Postgres databases are necessarily configured that way, and it's also less efficient. So in order for simplicity's sake, we wanted to design the system in such a way that it can always access the current field value of any updated field coming across the logical replication stream, regardless of toast. So what we did there was to store an additional copy of the current value of any field that we replicate, which is a form of stateful stream processing, which ended up working very well to handle that scenario. And then the last thing was handling different row identifier permutations. So Postgres has options in terms of row identifier information that can be recorded in the logical replication stream through replica identity. So you may be familiar with them: default, full, using index, and nothing. Default is obviously the easiest. We just use the primary key to identify a row so that when an update or delete to that row comes through, we can figure out what update or delete, what row does that operation refer to. But then there's also other settings like full and using index. Full can be used if your table doesn't have any primary key, for example, but you can use it regardless. And then there we basically just generate an ID from the relevant columns that are included. But there's also a setting called nothing where no information is recorded in the logical replication stream. And there we generate a random ID. If you have logical replication enabled, Postgres will block updating or deleting rows in that case. But we still need a random ID to keep track of the replicated rows, so that if the developer truncates the table, then we need to figure out which rows need to be truncated. So that's basically the conclusion here. We really want to help advance local first architecture adoption. Local first has several benefits for both developers and end users, and we're excited about the role that this sync engine can play in the local first emergent architecture. And with this architecture, we can provide sort of Postgres to anything bidirectional sync, currently focused on SQLite. And we're excited to see where this can go. So if you want to learn more about the sync engine, you can go to powersync.com. And I'm also happy to answer any questions.